Okay, class, we're up to chapter 4. And chapter 4 is about modeling. So you're gonna get practice modeling optimization models. And mostly it's gonna be linear, sometimes some discrete. And there's several sections of the classic problems that you see. So classic ones that you're gonna see, and you're gonna read this chapter and you'll see things about blending models, usually making some product and you need to several ingredients, blend them together according to some certain proportions. Another one is a set covering problem. We've talked a little bit about shipment, allocation, movement. So shifts is another good one, like HR, you need to schedule shifts of employees in the fire department or the police department according to certain things, and you don't want. Or airlines, they have restrictions about how many consecutive days folks can work or how many cross-country trips in a row. So you have easy to formulate those, who's working when, shift problems. And then there's some really cool ones in the back, mini-max and maxi-min problems that are super useful. I've used those a lot in my consulting and research. So you're gonna read through these sections, but the best way to actually model, I mean, seeing some more models and reading, seeing some of the typical methods or tricks is helpful, but the best way is to do it. And so this section, chapter 4, we're gonna slow down a little bit and you're gonna do a lot of team assignments that I've created over the years that students really like that help them with modeling. And so each week you're gonna have a team modeling project that you're gonna work on. It's a real problem and you can use software to also help you check if your model is correct and see if the answer makes sense. So I'm just gonna work a few ones here and we'll also use our software to give you a few more hints on how to input them into MATLAB. Okay, so I'm actually gonna go back to a couple that we've seen before. In chapter 2, there's a problem about covering site locations. So let me share the screen for a moment and we'll look at this problem, read it together. Okay, 22 here in chapter 2, a state Department of Labor wants to establish job training centers at 4 sites. So across the state, there's 5 regions, the Northwest, Southwest, Capital, Northeast, Southeast, and they only have funds to do 4 sites. And each site, there's costs associated with the land. Site 1 is rather cheap. It's only $43,000 to get that land to build it. Site 2 is the most expensive at $175,000, but site 2 does cover more regions. So maybe it's more central to the state. It covers the Northwest, so the little X means covers in that table. Covers the Northwest, Southwest, Capital, and the Southeast. Whereas say, for instance, site 3 would only serve the populations in the Capital region and the Southeast region. All right, so we want to minimize the total cost of getting these sites. Let's go from there and let's not use their suggestion for the decision variable, see if we can think about that on our own. So sometimes in working a modeling problem, you want to sort of work backwards and say, like, I would know the answer if, I knew which of those sites to use. So it's really a binary decision. Am I going to build in site 1? Am I going to build in site 2 and site 3? So that's a X, we can say Xi equals 1 if site I is selected, 0 otherwise. So right away, just from that, we haven't even talked about anything else, but from that decision variable description, we know this has to be in the integer programming class, a binary integer program. Okay, then next thing we want to do once we have those variables is we wanted to minimize the total cost. And site 1, if it was selected, was $43,000, so over like this. If it's selected, X1's turned on, that would incur a cost of $43,000. If it's not selected, no cost. Makes sense. And what did we have? 175 X2, that was the expensive one, plus what? 60 X3 plus, what was the last one? 35 X4. Okay, but there were constraints. It's not an unconstrained problem. we wanted to cover each region. So in the Northwest region, if site 2 or 4 was selected, we're covered. So we need, this is for the Northwest region. We need either of those to be turned on. So we say if the sum of those is greater than 1, then either one has been turned on. So it's a set covering problem in that sense. And we just keep reading down the columns of the tables and we'll see the next one, x1 plus x2 plus x4 greater than or equal 1. That's the Southwest region. Let's see, the next one was the capital, and that was only covered by x2 and x3, sites 2 and site 3. At least one of those must be turned on to cover the capital. The Northeast region, 1 and 4. And x1 plus x2 plus x3 greater than or equal to 1 covers the last region, so Northeast and Southeast. Okay, are we done? Objective function constraints, no other information in the problem except, what are we forgetting? Simple constraints. In this case, we say xi is in the set 0 or 1. That tells us it's binary. Remember, if we wanted to do the relaxation, so this is a integer linear program, right? Linear, integer linear program. But if we wanted to solve it as its relaxed LP, we would replace this with 0 less than or equal to xi less than or equal to 1. This is something that's commonly done to handle integer programs. Sometimes it's a good approximation starts by starting with the relaxed linear program. So these would be our lower bounds and our upper bounds. You would get a fraction between that. And sometimes that fraction is interpretable. And in a lot of my research, I will start with a binary, relax it, get some information from this, because maybe it represents like a percentage of in a particular problem. And maybe you can then round that solution. Maybe there's only a brute force finite number of ways of rounding the optimal to the relaxed, which is the rounded one may or may not even be feasible for this. If it's feasible, then maybe it's a decent approximation, or sometimes it's optimal if you're lucky. And there are cases in which you can prove that the relaxation will be optimal for the original problem. Okay, but we're solving the original one. And what I was trying to repeat is how are we going to put this in MATLAB? And we haven't done an integer linear program yet. So we'll get to use MATLAB's intlin-prog command. So before we do that though, let's pull up some of the matrices that we need. So our objective function is the vector f, which is 43, 175, 60, and 35. What else do we have? If we're thinking about, we're eventually going to use again intlin-prog and MATLAB, but we may need these lower bounds and upper bounds. We'll see what there's 4 variables, so that should be 4 by 1. Upper bound 1, 1, 1. We'll see what the syntax is for intlin-prog. I don't remember off the top of my head, so we may or may not need upper bounds and lower bounds. Remember though, for the lin-prog, and I'm sure intlin-prog is the same way, we need to write ax less than or equal to b. Those are the kind of inequalities had. All of ours are greater than, but we know if we just negate everything, negative, 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 that'll flip those. So we can write that our A matrix is, let's see, how many constraints? 5 constraints by 4 variables. So this should be a 5 by 4, x1, x2, x3, x4. And it'll be a 5 by 4 constraint matrix. First constraint picks up 2 and 4, except we want to negate it. And that means the right-hand side also becomes a -1. and B will be 5 by 1. Because there are 5 constraints. All right, so I just need to fill in 4 more rows of A. The next one is a -1, -1, -1. The third one is 0, -1, -1, 0. The fourth one is -1, 0, 0, -1. And the fifth one is -1, -1, -1, 0. All right, so let's go to MATLAB, see what happens with this guy. Okay, so we're in MATLAB. Here's our command window, and I've already entered some stuff. So I put in our F was the column vector of the objective function. I put in our A matrix. Remember, we needed A less than or equal to B, we think. So let's just check that. We go up into the help. We type Intlin Prague. Here comes the syntax for it. So we check, yeah, it is a min. We do need less than or equal to. We are minimizing, so our F is correct as it is, but this is why we flipped the A. We had A times X greater than or equal to B, we flipped it, so that's why we have negatives in the A. So here's our A matrix, here's our B. I wrote it as, just use the quick shorthand ones. Okay, and then there's this thing. So here's the simplest one. We have no AEQ or BEQ. But what is intcom? So we come down here, it says you can specify, X of incon, those are the integers. So let's look at their examples. So I think they have, okay, here's the first example. Suppose you had this problem, there's 2 variables of which only one, x2, is integer. And so you just set the index of that variable equal to 2. I'm sorry, incon is equal to 2 because that's the variable index that is integer. But let's just check a few more to make sure that we got the idea. Same thing here, x3 is binary, so you set incon to 3. And let's see. Oh, here's one where all the variables are integer, so you can just quickly make a vector 1 to n. So that's what I did here, 1 to n. Okay, and then what happened though? Incon needs to be, well, I thought it doesn't actually, it can be a row vector or a column vector. So I just transposed it. But then I started running the syntax. So I just copied and pasted the simplest type of syntax. And I thought that's what we had right here. Copied and pasted that and ran it and got an error. And it said, yeah, each element of incon must be in the range for the number of variables. And remember, there's only 4 variables. So I actually confused the number of constraints and variables. So I actually needed to set incon to be 1, 2, 3, 4. So I did that, ran it, ran our problem again, and now I'm getting that it's unbounded, and that didn't really make sense to me. So here's where I was saying, sometimes it means you've not specified the model. You've modeled it on the whiteboard correctly, but you haven't gotten it into the computer software right. And so then I remembered, oh, maybe this is, it used to have something called bintcon, and they no longer have that. That was for binary integer linear program. So in general, they're solving a linear integer program where the integer values can take on, it could be between 0 and 10. You could take on, and say x2, what was their example? Here, x2 is an integer. They're not saying it has to be binary, it's 0 or 1. They're saying it's just an integer. It could be 1, 2, 7, 11, right? So there was no restriction there. But let's look at their next example. X3 is binary. And what I missed when I was thinking about this, just running through it quickly, because x3 is binary, you actually have to force it to be between 0 and 1. So in that example, there was x1, 2, and 3. There are 3 variables. 2 of them just had to be greater than or equal to 0. So the lower bound was 0 on x1 and x2. And it was infinite. The upper bound was infinity on x1 and x2. But x3 had to be between 0 and 1. So that's what those bounds are. And for us, that means we want lower bounds because all our variables are binary. We want a lower bound vector for every variable. There's 4 of them. So I wrote 0 is 4 by 1. And then we want an upper bound vector, 4 by 1. Okay, now I try again. and I copied the documentation. What's the syntax? Okay, when we have upper bounds and lower bounds, so I just copied this one. Input it. And I knew it was going to give me an error, but I wanted to show you why. So when I copied that, it's like, hey, what's A and Q? I don't know what that is. Well, we don't have any A and Qs, so we actually enter a empty matrix. So I defined A and Q to just be bracket bracket, which means it's empty. That's telling MATLAB there are no equality constraints in this. There are no equality right-hand sides. Now that you've done that, you're finally done setting up everything that MATLAB now knows what you've written on the whiteboard. You've got it in MATLAB. Okay, now what happens? The run that same command again. It terminates. It tells you the optimal objective value is 95. It's found an optimal solution, and here is the optimal objective, optimal solution. Don't use site 1. Don't use site 2. Use sites 3 and 4. You could check by hand that setting x3 to 1, x4 to 1 satisfies the constraints and gives an objective value of 95. Is that the only optimal solution? That we don't know. It might be multiple optimal solutions, and that's a whole nother area of my research and also that other folks are interested in. It'd be nice to know if they had choices, because maybe there are secondary conditions about the sites besides just the cost. Maybe you could go in and say, maybe it's number of population served, or it could be secondary considerations in this problem. Okay, we're going to try one more. Next one we want to look at, we have already seen before too. It's number 35 in chapter 2. The railroad needs to relocate cars from 5 regions. And so here's where the cost of moving one car from region 1 to region 2 is 10, from region 1 to region 3 is 12. And we have how many are in each region now and how many we need. So like right now in region 1, there are 115 cars total, but ultimately we need 200. There's more in region 5 than we actually need. So we need to move some out. And we're going to define variables xij as the number of cars from I to j. And we modeled this last time, and then I want to talk about ways of putting this into MATLAB. Okay, so here's the model we were practicing then using our shorthand summation notation. We said that we would take Cij times Xij for all 20 entries in that table. We didn't need anything to define variables along the diagonal. So we do this for I equals 1 to 5, j equals 1 to 5. Actually, j equals 1 to 5, 2, I not equal to j. So we're really summing up 20 things in this sum, 20 coefficients that we're interested in. And then we had these constraints about, like in region 1, you started with 115, you needed to end up with 200. This represents all the cars leaving region 1 from 1 to 2, 1 to 3, 1 to 4. Those are all the ones exiting region 1. So we're going to subtract those. And then we're adding in how many come into region 1. So they could come from 2 to 1, from 3 to 1, 4 to 1, 5 to 1. And that has to be 200. So we did that for all 5 regions. And all of our variables are greater than or equal to 0. A couple ways of defining this to set it into MATLAB. You could say, not say I not equal to j, you could actually form 25 variables and force the diagonal ones or the I ones to be 0, like manually in MATLAB. Or you could only use the 20, like we were talking about, the off diagonal elements in that table or that matrix. You only use those. So let's think about doing it that way and how we were going to pick off things to put them into MATLAB. So you actually have a choice here for, and this was a decision where to put this. Maybe I can squeeze it down here. We're going to define x to be like this. We're going to pick the order. We're going to go column wise. So x is a matrix of unknowns. X again is a matrix. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5.
So x1, 2, we don't need one there, x1, 3, x2, 1, and so on. x3, 1, x4, 1, x5, 1, don't need one, x2, 3, right, and you can fill that in. If we pull those off column wise and put them in a vector, then we'll have x2, 1, x3, 1, x4, 1, x5, 1. The next column will be x1, 2, x, skip and down here, x3, 2, x4, 2, x5, 2. Third column, x1, 3, x2, 3, x3, 3, skip, x3, 4, x3, oops, sorry. 4, 3, 5, 3. Fourth column will be x1, 4, x2, 4, x3, 4, x4, 4, skip, x5, 4. Last one, so 4, 8, 12, 16, last four of them will be x1, 5, x2, 5, x3, 5, x4, 5. So again, we have decided this order. That was somewhere, that's our choice. You could have decided to put them in row order. You could have just done some random order, but do something sort of makes sense. So I'm going to do them column wise. And now when I'm pulling off the C, that or becomes F, usually what we call it in MATLAB, the F vector will be the columns in that C matrix. So C will be, where to put it? It'll be okay if I move some of this, erase a little bit of this. F would be, just again, got to go in the same order. So we're going to go down. It's 10, 12, 17, 35, 10, 18, 8, 46, 12, 18, 9, 27, 17, 8, 9, 20, 35, 46, 27, 20. Okay. And again, this is a 20 by 1 vector, 20 by 1. First, second, third, fourth, fifth. The components, we're just ordering them because we might need this later. 10, 11, 12, 13, 14, 15, 16, 17, 19. Okay, what else do we need in MATLAB? We're going to need, we're going to do linprog, right? And we're going to need lower bound, upper bound. So we will need a lower bound vector of zeros. That is 20 by 1. We need an upper bound vector, infinity times ones, which is really saying there is no upper bound, which is 20 by 1. All of those were equal. I erased some of the all equalities, which means A is empty and B is empty. Another easy one to put in here is BEQ, which would be the right-hand sides. The first one was equal 200, right? Minus 115, so 200 minus 115 is the right-hand side. The next one was 500 minus 385. So whatever these constants turn out to be, put those in a vector. 800 minus 410, 200 minus 480, 300 minus 610. All right, so those constants go in the BEQ. Now, the hardest part is the AEQ, right? Now we have to pull off on the first, there's 5 constraints and 20 variables. So first of all, what's the dimensions of AEQ? Because all those were equalities. The only constraints we have are equality constraints. There's 5 of them. So the dimensions are going to be 5 by 20 variables. So I don't need to make some more space here. Okay, erase this one. We know what that is. Erase this, maybe make some room here. And this. All right, AEQ. Remember, each column corresponds to our variables. So that's X in this order, the order that we described. X21, X31, X41, X1. And we can think about that as a block. The next one, x1, 2, x3, 2, x4, 2, x5, 2, right, and so on. The first row, and there's only 5 rows here, 1, 2, 3, 4, 5, and each corresponds to a constraint. The first constraint, you need to pick off the coefficients and put them where they go. Largely, AEQ is a bunch of zeros, right? So you could start by filling it in by making a 5 by 20 matrix. And then we'll go ahead and fill in each individual component. So like, for instance, AEQ 1 for the first row, where's the first non-zero that I get? There's this one, -10. So I need to put a -10 in the 1, 2 position, which is over here, which is actually the 5th column, right? So 1, 5 gets a -10. But it also appears, 10 appears over here in 2, 1. So AEQ 1, 2, 1 is the first one, should be a 10. So like we know this has to be a 10 and this has to be a -10. And then we move on to the next coefficient. -12 needs to go in the 1, 3 position, which is actually over here, the 9th column. Right. So 1, 3 should be -12. And I can write that, just tell it, go into the matrix, which we initialized as zeros, in the 1, 9 position, put a -12. But also, there's a +12 in the 3, 1 position. So 3, 1 is the first row of this matrix, and the second column, put a +12. And you just continue picking these off and building AEQ, the non-zeros one at a time. That's actually the easiest way to enter it here. And so I want to, let's pause and go back to software. All right, if we go back to MATLAB, we need to start entering these things, right? So we said that, let's clear all, clean up our workspace, goes away. If we want to, we can clear this whole command window. And we said there were no inequality constraints, so, and there were no inequality right-hand sides. So we initialize those as empty. We said that lower bounds, there were always 0 for all of our variables. There are 20 variables. Upper bound is infinity times 1s. There really are no upper bounds. C was a column vector, 10, 12, 17, 35. Oops. And just check the dimensions. Yeah, I got everything right. It's 21. You can check it. BEQ, we have 5 by 1 vector. It's 200. Oops. 200 minus 115. That is 500 minus 35. 800 minus. I'm just letting MATLAB do the arithmetic there rather than me. 200 minus 180 and 300 minus 60. And then we needed what else to do this? Because again, we're doing lane progress, just make sure what we need. Syntax. So we are going to be running this one here.
Oh yeah, I entered C, so we can just call that C. Okay, and then the only thing we need is building this AEQ, and that was the hard part. Like AEQ, we're gonna initialize it as zeros. What were the dimensions? 5 by 20. I'll suppress the output. I can see what matrix of zeros. And then you need to start looping through. And so maybe I'll pause the video and enter all of those. I only put a few on the board. I'll enter them all here for a moment and then come back. Okay, I've got those entered in MATLAB. Let me just show you what I did here. All right, so we initialized AEQ to be a bunch of zeros, started putting in the coefficients row by row. And so like I entered all of these right here, got this first row. Here's the second constraint, got the next row, just did them one by one, displayed them. And here's AEQ. And then I run it and I get a solution. And I'm looking at the solution and it doesn't make sense, right? That they're only moving 5 cars. This would say, which one does that correspond to? This is 1, 2, the third component in the X vector corresponds to X41. So it's saying you move just 5 cars from region 4 to region 1. And in total, we're not moving very many cars. And just think back to the numbers. We had like in region 1, 115 cars and we needed 200. In region 5, we had like 600 and we need 310. So it should be more movement. So something's going wrong here. So I had to go back and think. And I took a little bit and then I remembered those constraints on the board, those are actually, I shouldn't have the cost coefficients in there, right? It should be, let's go see that first. It should be the number, the XIJs don't have cost coefficients. It's just the number of cars moving. So I should have in that first parentheses with a negative, all those coefficients should be 1. And in the plus parentheses where we're adding all the cars coming in, there shouldn't be any cost coefficients. I don't know what's thinking on that. They should all be 1s, right? So what I had to do, rather than rewriting all of these entries, not that that took that long, I just had some quick shortcuts. So I made a new AEQ matrix, the correct one I'm calling A2 EQ. And first I said for any AEQ that was greater than 0, I'm going to just do this logical statement. And I turned all those to 1s. Right, I don't actually want those. Back up here. Oh, I don't want that to be 10, 12, 17, 35. I want it to be 1, 1, 1. I just want to sum up X21 plus X31 plus X41 plus X5. And that's the number of cars leaving, not the cost of such a just the number of cars. The cost is in the objective function. Okay, so I did that and I got part of my matrix that I wanted and those are in the right positions. And then I did the same thing. I took all the negative values in this messed up AEQ and just turned in the -1. And so I did that with this logical command here. And now here is the A2 matrix. This is what I want. Here's the number of cars, X21 plus X31 plus X41 plus X51. That's the number of cars leaving region 1. I'm sorry, entering region 1 from 2 to 1, 3 to 1, 4 to 1, 5 to 1. Here's the number of cars leaving. That's from 1 to 2, 1 to 3, 1 to 4, 1 to 5. Okay, so this is the right AEQ. Now I run my linprog again, using all the things I already entered. And, oh wait, it didn't work because I forgot to put A2 in there. So I just used the previous one. Now I did A2, the correct equality equation matrix. Okay, now we get this. This, at least these numbers make more sense, right? They're about what we would expect given the parameters of the problem. And now you have to translate this back to your original variables, right? This is the fourth component is non-zero. And so in our definition, the fourth component was X51. So this is saying set X51 to 85 cars. So from region 5, you're going to send all those extra cars you had, all 85 of them, go to region 1. Region 1 had 115, it needed 200. It's clear to see it satisfies that constraint. And then we go down to 1, 2, 3, 4, 5, 6, 7. The seventh one corresponds to X42. So you can set that to 115. And let's see, what's the next one? 7. 8, 9, 10, 11. The 11th one is x4, 3, and the 12th one is x5, 4. Sorry, 5, 3. All right, so those tell you, those are the only non-zero ones. That's the movements you're making. If you wanted to see the optimal objective function, you would call it whatever you want for the objective value. You can say object value. It'll run it and spit out, here's the cost, $11,000 to move those cars in that way. Okay, so that's good practice to see what it takes to enter something, and also to see like common places to make errors. I did it, I haven't used WinFrog in a while. I've been using some industrial software. So I got to see like, hey, wait, that doesn't make sense. Let me go back and you got to walk through that process. And now I want to show you some other software that is used. So let's go to our book. Okay. In our book, in chapter 2, I think there's a couple places and also throughout. So this edition, Ron Rardin added some AMPL, AMPL code. AMPL's an industrial software. So we're using MATLAB. Pros and cons of MATLAB is free for us at the College of Charleston. But even past that, it's a much less expensive software, like maybe talking hundreds of thousands of dollars to ask your employer to get you MATLAB. You can also get a student version for very, very cheap for a very long time. And it comes with, I think I mentioned this, all this great support, staff. You can just email, chat with folks. There's a whole community, network community, people that make code for it. It's because it's a commercial software program. It's not like R, where you could download a program for linear programming using R, which is freeware, but there's no guarantees what's happening. There's not much documentation. So because MATLAB's commercial, it's on the, you can trust what you're getting, but it's on the cheaper end compared to Ample, Gurobi, Express, Cplex. These are some Dash. These are some of the industrial ones that cost not in the thousands. We're talking tens of hundreds of $1,000s to get those. So easy to pick up and learn if you decide you want to work for, say, a national lab, national security agency, airlines, airline industry, Amazon, shipping, USPS, UPS. If you're working for those, they're going to have one of these industrial licenses to industrial software. Now, the advantages of that, again, very easy to pick up that language, and you'll see why. Like, here's Ample code. You define some of the parameters, or for us, those would be like the cost, the CIJs, that are just entering all those by hand in MATLAB. Okay, well, you enter those, or you can like import it as a matrix, or it could be from an Excel spreadsheet, a table. It gets imported rather easily. So this thing got parameters, but then here's some of the code. Okay, so then you actually define variables, and you don't need to do what we did in MATLAB, where I had to make that definition of the x's. This was x21, x2, and so on. You just say xj for all the columns, greater than or equal to 0. You don't have to fool with like the upper bound, lower bound part. You want to maximize. For us, we would be doing CIJs times XIJs. So you actually write it like closer to what we write on the board in these programming languages. And what they do is they're able to take that language and create the A matrix, create the AEP, because it's a very systematic pattern usually to doing that. And here's some constraints. Subject, you have to say subject to, summing all the columns, AIJs times XIJs, that's equal RI. So take a look at these pages just to see what's out there. There are some student licenses. So again, if you feel like you just love this stuff and this is going to be your career path, it's a good idea to ease yourself in. We're going to learn plenty with MATLAB. And again, my feeling is it's very easy to translate those. But you can get student, check it out, Google for student licenses of Express, Dash, Cplex, AMPL, and there's lots of short manuals that actually solve scheduling problems and show you the Ample code, show you the Gurobi code. Often those software don't have great help desk, don't have very good support, but they do have just a library of examples that are helpful. So you just learn by examples on your own. Okay, so pages 69 through 72, and then there's some more at the end of the chapter, 85, and the chapter problems. And throughout, we'll see these the sample code. Okay, and then let me go back one more time to the MATLAB. I mentioned like the structure in A. So let's look at our correct A, AEQ, A2, EQ. So maybe you notice that there's a block, a row, a sub matrix or sub vector here in the first row of ones. That happens again in the next row, just shifted over 4 units, and then the next one shifted over 4 and shifted over. And that's what I was saying about the structure. So that's how these industrial commercial codes can read that summation stuff and make their own A's rather quickly. And you may need to do this in a couple of the modeling ones in this module to make little loops in MATLAB to rather than by hand. And so I was able to do this up here with these kind of, wasn't too much typing. You know, I did them row by row. There's only 5 rows. You could do that. But if you notice the structure, then you can often make loops that'll form your matrix much faster. Notice the positions of the -1s also. There's some structure to those, like here, like a diagonal. So you may see that you can divide your A and AEQ into submatrices with particular structure and patterns and make loops to easily build it. So if there's one comment. Oh, yes, it was. So on a couple of these upcoming group modeling problems, you have to work with your team and really test it out. And a great piece of advice in general, one was figuring out the definition of decision variance by sort of working backwards and saying, like, okay, imagine this was solved, what would I be telling the client? I'd say, use this site location, use that site location. Okay, so then I need decision variables related to that. But the second piece of advice is breaking a problem down into is there a smaller version? Like, well, this one had 5 railroads. Maybe you say, what would I do if there were only 3? And then maybe seeing that there's structure and forming the A for 3 regions to move it between rather than 5. You're going to work on one that has to do with Sudoku puzzles and trying to solve those using linear and integer programs. And Sudoku puzzles are 9 by 9, but what's a smaller version? Is there a smaller version you could think about? Does that help you answer the problem? Figure out the hints and structures from that smaller problem and work your way up. And those you can enter by hand, and then you start figuring out, okay, well, I definitely have my constraints right for the small one. Let me see if I can amp it up, even though I can't figure out the looping to make that A and AEQ just yet. But I can do brute force entering by hand with a small example. Okay, well, I think it's going to be a fun module. So enjoy modeling. It's really empowering.